Thank you very much. It's a great honor and a pleasure to be here. And I must admit, a bit intimidating to be in front of all you people, but I wouldn't be able to do it without the help and support from Sergei and Jacek that helped me with my scanning helium ion microscopy, and my supervisor, Jonathan Wheeler. And for those of you that have arachnophobia, don't worry. I think I have removed most of the scary spider images. So let's begin. So the first thing to do is to ask yourself, why is spider silk even important and interesting to work with? So spider silk is this fiber that is about 20 times thinner than a human hair. And it's this thin, and it has an ultimate strength of over 2,000 megapascals. To compare, steels that are used in building rockets and missiles have the same ultimate strength. As well as being very strong, spider silk can extend more than 150% of its own length before fracturing. And all of this in this material are made at room temperature. So now we need to figure out why this biomaterial has these amazing properties of being very strong and elastic. And today we're going to try to find the link between these macroscopic properties and link between the microscopic structure of spider silk. So first of all, we're going to look at the structure of spider silk. And spider silk is proposed to be this fiber that consists of 3 outer layers, a lipid layer, glycol layer, and skin layer, and then 2 inner protein cores. So the first thing we did to look at this layered structure is that we labeled with a hydrophobic and a hydrophilic dye. We saw that the hydrophobic labeling labeled the outer layers, we think mainly the lipid layer, and then we saw that the hydrophilic dyes labeled the inner protein cores. As if you notice here in this image, we see that there's a shadow between the 2 layers. This might be because of the way rhodamin B binds to specific proteins. Another way of looking at spider silk, another technique we use, is coherent anti-stress Raman scattering microscopy, which is a technique that enables you to look at specific chemical bonds, and it is label free. So in figure A, we are looking at the CH2 symmetric stretch, which is highly present in lipids, and as well as other organic compounds. So here we see a very strong signal at the edge of the spider silk, which is our lipid layer, and we see a very strong signal at the center, which is our protein core. And again, we notice that we have this shadow between these 2 layers, which may be because of the chemical composition of this layer, or because of the structure of spider silk. If we look at figure B, here we're looking at an autofluorescence emission, and from an overlay of these 2 images, we saw that this autofluorescence signal comes from mainly the protein core. So in order to get information about the protein core, one can just simply look at the autofluorescence signal. So these 2 previous techniques were quite limited by the resolution. So in order to look at the nanoscopic structure within the spider silk, we use scanning helium ion microscopy. In short, this technique is where we have helium atoms that are ionized to helium ions and then focused onto a sample. The interaction between the helium ions gives way to 3 detection possibilities, and in our project we looked at the secondary electrons. The secondary electrons are made by the helium ions exciting and ionizing the electrons within the sample atoms. And one of the advantages of helium ion microscopy is because the helium ions have a small wavelength and a small interaction volume, we can get a very high resolution. So here we have an overall image of 2 spider silk strands in the middle, the 2 black strands, and these have a diameter of 2.4 micrometers. As you notice, the spider silks are completely black, and this is due to the lipids being non-conducting. So we get an accumulation of positive charge, and this inhibits the escape of secondary electrons. So another advantage of helium ion microscopy is that it's possible to cut or etch away layers of our sample using surface sputtering. So as we see here from image 1 to 6, we see that we remove layers from the left side of the sample. And throughout these removal of layers, we are able to see the protein fibrils that are present within the protein core of our spider silk. So here we see an overall image of the 2 spider silk strands, And you can see with the light spot is where we have actually cut away in our sample. And we found that within this spider silk with a diameter of 2.4 micrometers, that the fibril diameter is 28 nanometers. Then we wanted to compare helium ion microscopy with scanning electron microscopy. The problem with electron microscopy was that if we wanted to look at the protein fibrils, we had to remove the outer layers manually or chemically. Here we have removed the outer layers manually, and again we see these protein fibrils parallel to the silk strand. So here we have a spider silk strand of 5.4 micrometers, and we found that the protein fibrils within this spider silk were 104 nanometers. So now that we have a better understanding of the structure of spider silk, we would like to look at the biophysical properties of more specific components within the silk. For example, the phase of the lipids. So we do this by using a fluorophore called laudanum. So when laudanum is excited, a dipole within the molecule is induced. This dipole then forces rearrangement of the solvent molecules surrounding it. If we, for example, have a gel phase, then the lipids are so densely packed that they shield laudanum from the water, surrounding water. And this gives way to blue emission. If we, however, have a liquid phase of lipids, we have more water present, and then this rearrangement of the water molecules causes energy. This causes a redshifting in the emission line, and we have re-emission. So what we do then is that we can calculate a GP value, which is basically the normalized difference between the blue and green emission intensity. With this GP value, we can then quantify the phase of the lipids. So within our spider silk, we found that the GP value was 0.2, which corresponds to a liquid order phase. This was quite interesting because the lipids within spider silk are these long carbon chain alkenes of up to 34 carbons, and we would expect these lipids to actually have a gel phase. So there's some more work to do as to figure out why they seem to be in a liquid order phase. So now we want to actually find this link between the structure of the spider silk and the macroscopic properties. So what we did is that we built this force pulley that is able to measure the force and the elongation of a spider silk, as well as we're able to mount this force pulley on a multiphoton microscope. This enables us to image the spider silk while we elongate it. So we wanted to look at how the structure within the spider silk changes upon elongation. And we did this by rotating the excitation, rotating polarization of the excitation light, and then monitoring the intensity of the emitted light. As we see here in these images, the arrow represents the angle of the excitation light, and as you can see that the intensity of the emission changes when the angle changes. So the first thing we did is that we wanted to look at the proteins, and as I mentioned earlier, in order to look at the protein structure or protein core, we could look at the autofluorescence signal. And the first elongation to look at is obviously the no elongation. So here we see a typical data set where we have the normalized intensity as a function of the angle of the excitation line. And as one can see, there is no visible dependency on the angle, meaning there is low structural order of the dipoles within the proteins. If we, however, stretch a spider silk, we start to see that there are specific peaks where at specific angles where the emission intensity is at a maximum. And in these intermediate steps, we also see this trend. So we see that we have a maximum at 60 and 240 degrees, which corresponds to when the excitation light is parallel to the spider silk strand. So we did the similar experiment for the lipids, where we looked at the laudanum emission. And here we see that for every elongation value, there's actually an angle dependency. And here we see that we have a maximum at 160 degrees, which corresponds to when the excitation light is perpendicular to the spider silk strand. So in conclusion, we have found that we have a hydrophobic shell and a hydrophilic core. However, we also found that we may have this layer in between that we have not been able to characterize. We We have also found that we have these protein fibers, or fibrils, that are aligned parallel to the spider silk. And we also found that the size of these fibrils changes with the size of the entire spider silk. Then we also saw that the dipole moment of the lipids is oriented perpendicular, as we expected, to the spider silk, and that these are in a liquid order phase. We also saw that there was a low structural order of the proteins before elongation, but this structural order increases when we stretch the spider silk. This can be explained by knowing that within these protein fibrils, they consist of beta sheets that are connected by alpha helices. And when the spider silk is not stretched, we have that these alpha helices have dipole moments that are randomly oriented. When we have a stretch of spider silk, we stretch these alpha helices, and the dipoles within them go in the same direction. So since this is a Future of Biophysics symposium, I'd like to talk about my future of biophysics. So what I really want to do is to be able to use the tools that are available in biophysics to learn about the materials we find in nature and actually exploit them. And from that understanding, being able to construct our own materials with the same amazing properties. And how this can be done is by combining different fields with biophysics. For example, combining proteomics and microscopy, and combining this with also material properties. Thank you for your attention.